Hello and welcome to the webinar, 40 Years of Water Quality Statistics, What's Changed, What Hasn't. My name is Dennis Helsel. I'm with Practical Stats, and I will be the guide for this webinar. Thank you for coming. There are actually many more people signed up than can attend, but we still don't have a full group yet of the people who can attend that are here yet. So I usually try to stall a little bit at the beginning and it'll give people a chance to sign up. Let me give you a few pointers as we're waiting for people. First, if you're having trouble hearing me, that is usually because somewhere between me and you, the connection isn't great. And generally, the computer voice over IP works better than a phone. But if you are using wireless and your wireless connection is shared by a whole bunch of other people in the office, then you may not be able to hear me well. And if that's the case, you can go ahead and dial in. The dial-in number was given to you with the invitation and the email that had the link to sign up. So actually to join today. So you can go there and find that. It may be also visible on your control panel. So let me tell you about the control panel a little bit on the side. It helps you to change a few things. Let's see, the things that are important for this webinar for you are the questions pane. And that's where you would type questions and send them in. And at the end of the webinar, I will answer as many as I can. With the number of people that are going to be with us today, I'm sure I will not be able to answer all of them. So I will answer as many as we have time for. I want to try to keep it to an hour. And then I will post answers to all the rest of them in a file. It's usually an Excel file on our downloads page. And so you'll see the URL down at the bottom here, practicalstats.com, info to use, downloads.html. And you will also find a handout there if you are listening to this on a recording. If you're listening to it live today, the handout is right here on the handouts section of that panel, and you can just click there to download it. So it's a PDF file at 2 per page of all of the PowerPoint slides for today. So I think that's the main things other than the audio. Again, the computer audio works best for most people, but if you are having problems, you can shift it by clicking to phone call and dial in using your phone. All right, let's begin. So we are going to talk about water quality statistics and how that field has changed over the last 40 years. That presupposes I was around doing this 40 years ago, and I was. So I'll give you my view. I've got 3 main objectives for this. And the first is to present 5, I'll call them bad habits. They could be misunderstood practices that after 40 years are commonly still done today. So sometimes I describe these as zombies. These are things that were dead a long time ago in terms of their usefulness. But in environmental science, they're still walking around and being used. So I'd like to give you 5 of those today, point those out to you, encourage you not to use them anymore. I'll do that by number 2, presenting current methods that have replaced them in statistical practice and should replace them quickly in your work. And then finally, look ahead a little bit to discuss 1 or 2. It'll be primarily 1 direction that statistical practice is heading. And if it goes in that direction, it certainly will impact your work. And so I want you to be aware of it and look out for it and maybe adapt to it. So what has changed overall is that there's a new book coming out. It's the 2nd edition of Statistical Methods in Water Resources. It now has and I guess I'm presuming that most of you are familiar with the original version. It now has 5 authors, in addition to Bob Hirsch and myself, is Stacy Archfield, Karen Ryberg, and Ed Gilroy. And the 5 of us have modernized that text, and that's been a several-year effort. And it is coming out, and we are assured it is coming out sometime in 2019. I'm guessing June, but I've guessed about 3 times before, and it's never made it in those 3 times. So my track record isn't good, but I'm hoping, I guess is the best way to put it, it'll be out sometime in June. If you would like to know when it's out, you can get on our announcement list. It's also our newsletter list. It's a free sign up. It gives you an email once a month now, approximately, no more than that anyway. And you'll have an opportunity at the end of this webinar to sign up for it. So I will just tell you if you'd like to do that, and you don't have to by any means. It will be announced when it's available. It will be a free download from the USGS publication site and also from our practical stats site. So there's the URLs for that. And it talks about these changes that we're going to talk about today and a lot more. And so it's completely revised from the original edition that came out first in print in 1992 and then as a PDF in 2002. The USGS is certainly putting out a PDF file, and that will be free. There are rumors that they will be putting out it in a book form. I haven't gotten those confirmed yet. I have hopes that they will. If it's a print book form, a hardback book, then that will not be free, but they do price those things so that it just covers their costs. So I don't expect it to be too high, but I don't know what that will be. And it's not my decision. So that book is coming out, and that is something about what has changed in statistics. There's a lot of new things in there. So we're going to talk about a few of those today. So the first thing that has not changed, that's still walking around dead, is an idea called robustness. It's robust. And this is referring to primarily t-tests, ANOVA, and other parametric tests, which were developed back in the 1930s, 1940s. And there are papers that you will see and websites that you will see that claim that these things are robust and therefore should be widely used in a large number of situations. So what does robust mean? To most of us, robust means that it's, like strong coffee. It's really good stuff. But it has a much more specific meaning in statistics. And so it does not mean it's generally a good thing, even though that's how it's been used by these 3 authors. So Montgomery and Loftus back in 1987, they have since recanted their statement. Johnson in 1995, and there's a big discussion of his work in the new version of statistical methods in water resources. So that'll be fully discussed there, and I'm giving you the short version today. And I would have liked if that was the last time I had seen it, but actually I saw it in an article about 3 or 4 months ago by 2 ecologists. So this claim that the t-tests and ANOVA are robust and therefore should be used all the time only looks at one type of problem. And so robustness in statistics has a specific meaning. That meaning is that it will not have more than it should of false positives. In other words, if you run a test and with an alpha of 0.05, the test should perform so that it would not give you more than 5% of the results, being that there's a signal, that there's a trend, that there's a correlation, that there's an exceedance of a standard, whatever the test might be testing for. It should not give you a statement that that happens when out in the field it really does not happen. So that would be a false positive, and that's what robustness is, that the test does not give you too many false positives. But it says nothing at all about false negatives. And so the problem with these tests, the t-tests and ANOVA and other parametric tests, are that their power is low, meaning that it gives you a lot of false negatives under certain conditions. And those conditions are that the data do not meet the assumptions. They're expecting data that look like a normal distribution, that are shaped like a nice bell-shaped curve, that are symmetric, that you can be as easily as 2 standard deviations above the mean as 2 standard deviations below the mean. And that's not what concentration data, that's not what water quality data, and it's really true about air quality and soils chemistry as well. These types of things in the natural world don't look that way, and so they generally are skewed. And data that are skewed are not normal, not normally distributed. They're actually very normal in the sense of frequently occurring. And so these tests don't work that well on those, and particularly they don't see signals that are there. They don't detect trends. They don't see exceedances from a standard. They don't bring in variables into a regression equation when they should. So that lack of power is a big issue. There are other issues listed here. I won't go into all of them. I'll go into maybe one more, but the power is the big issue. And so what that means is when you get back a p-value, and we'll talk about p-values later, it's too high. It's going to tell you that there's not a signal when there is one, more than it should. So it's giving you false negatives. So that's the big problem with them, and that's not considered at all if someone just grabs the word robust from the definition of a test and says that means it should be used all the time. So there is something else, and this goes along with that idea of robustness, the central limit theorem. And the central limit theorem says that, well, I won't go into it in detail. I don't want to put you to sleep. But it does say that you can ignore that non-normality if you have enough data. And so you've probably heard the rumor that around 30 or so is big enough, and it is just a rumor. It's actually a false rumor. How much data you need to not worry about non-normality is a function of the skewness of the data. The more skewed, the more non-normal, the more data you would need for this situation to occur. And for the typical skewness pattern in water quality data, and it's true for air and soils as well, that's upwards somewhere around 70 or 100. And if you're doing group tests, that's the number of data per group. So it's much larger than some people think. So that's the problem. Before I get to some of the changes, I want to do a poll. They tell me that this is helpful for people listening. So here is a poll. And the question is, have you ever used a permutation test? And you can select either yes or no. It's pretty simple. So why don't you go ahead and do that. All right, that's a lot of you that have voted. So it looks like there are about 40% yes and 60% no. That's amazingly, I wonder if they rounded that. I don't know if they did, but so that's about what I would have expected. It's still not widely used. So let's see why they should be used. There are methods called resampling methods that are newer in statistics. These were developed in the late 70s and during the 80s. They're still being developed today. The hypothesis test versions of them are called permutation tests. The intervals, and there's other regression related uses for them, but intervals are one of the primary uses, are called bootstrapping. So these are methods that require the computer to redo things thousands of times, and computers today do that very fast. So they work very well. They are distribution-free methods. That's another term you might not be familiar with. It just means you don't have to assume any particular distribution or shape to the data. They work well regardless of that. So older non-parametric tests, tests that are based on ranks or percentiles, are distribution-free, and these permutation procedures are distribution-free. So there's a book One of the classic books in statistics back in 1991 on intervals by Hahn and Meeker, who said that one might ask, when should I use distribution-free statistical methods? The answer, we assert, is whenever possible. If one can do a study with minimal assumptions, then the resulting conclusions are based on a more solid foundation. And I've seen nothing in that 30 years or so that would change that opinion. So here's just an example. This was a small data set of 16 observations, 2 groups, split into 2 groups. They were concentrations in groundwater, as I remember, and it was before and after some remediation. And the t-test returned a p-value of 0.14. That number is higher than 0.05, which is the classic cutoff. We'll talk about cutoffs later. But the classic cutoff, and so one would conclude that there's not enough evidence in the data to say that there's a difference with the t-test. However, with the same data and the same objectives, testing differences in means that the t-test has, we could run a permutation test. And the p-value for that for the same data was 0.0018. So orders of magnitude lower, and certainly saying that there's a strong enough evidence to say that the means differ between these 2 groups. What's the difference between those 2 numbers is just the test, and it's just the power of the test. This is an illustration of the loss of power of the t-test. These data were quite skewed, and so the t-test does not work well on them. So that's just one example. Here's a second example. I put this in because I looked at it about 40 years ago. When I first came to work for the US Geological Survey, I think they didn't quite know what to do with me to start with. And there was a study that had been started by a woman who did a fantastic job of collecting data out in the eastern part of Ohio, and collected data on low flows in streams at sites that were unmined upstream, or that had abandoned coal mines upstream, or that had reclaimed coal mines upstream, and took various measurements of parameters. This is one, iron concentrations. There are 50 observations in each group. And so that's the main thing I want you to think about. It's above 30. And the data were non-normal. They're not equal in variance. You could take logs. I won't go about in this too long, but when you take logs, then you've just changed it and you're no longer testing for differences in means. So if you really are interested in means, that's not an option open to you. So you can see that unmined is less than reclaimed, and reclaimed is less than abandoned. There should be a less than symbol in there, but this is not seen by the ANOVA. Here's the picture. These are box plots, and you can see that that relative difference certainly looks like it exists. If you did an ANOVA, the p-value is 0.10. If you did a permutation test on the same data, p-value is 0.001. So same objective, same data, big difference in results because the data are skewed. So this loss of power is a serious issue. It wasn't really solved until there was computing power to compute permutation tests. Another version of these resampling methods is called bootstrapping. Last year in 2018, Bradley Efron, the professor of statistics at Stanford, was given the International Prize in Statistics. That's like the Pulitzer Prize, or maybe even more prestigious in statistics, for his development of the bootstrap back in 1997. So this is not a new method. They, in awarding it to him, went through a whole bunch of journals. This would have been about a year ago, and looked at the numbers of references. I'm sure it was just a text search to bootstrap in different disciplines. And in agriculture and biological sciences, that was pretty large, 44,000 and some. It was one of the larger ones, actually might be the largest one. Environmental sciences were at 14,000, which is actually better than I thought, and certainly more than some others, although there's no evaluation of size, numbers of people, and numbers of papers published in each of these disciplines, I don't think. 14,000 is not bad, though. But it's about half that was in mathematics and medicine and so on. So Other people are using it. It sounds like 40% of you are using it. So the question is, for the 60% that are not, why not? If you don't know about them, just pick up a more recent book on statistics. Go through the table of contents. If they don't discuss permutation tests and bootstrapping, get another book. They obviously will be in the new version of Statistical Methods and Water Resources. They are in our Applied and Minor Environmental Statistics course. That's an online course these days. You could certainly take that at some point. So there are options for learning about them. You can just do a browser search and find a lot out about those procedures, and you should. Here's just a picture of the bootstrapped confidence interval that's in the blue on the graph to the right, and the old t-interval that's in the red. You notice the bootstrap interval is a lot shorter. That's another way of visualizing the difference in power. That the shorter is better. It can do with the same amount of data a better job of showing where the mean might lie. All right, second zombie. How few observations can I get away with? I think it's usually asked to me about, in a way like, how many observations do I need? But the underlying statement really is usually how few observations can I get away with. So the problems have been that guidance documents really haven't helped in the past. There's EPA 2008 guidance that says n greater than or equal to 30 is large for sample sizes. That's not large. It's often not enough to overcome these problems with the older tests, and that back then was probably what people were using. So this is an urban legend. It invites people to collect fewer than 30 observations because they don't need to do large data sets. And that's too bad, because often you need something on the order of 30 observations or more. Groundwater studies that I have seen often are done with 2 samples per year, and after 2 years, so 4 samples total, they want to compute trends. For surface water quality, trends are computed sometimes by doing annual sampling and collecting it for 5 years. You're not going to find a trend in either of those cases. You're not going to reject the null hypothesis of no trend, no signal. It's not that there isn't one out there, it's just that you haven't done enough work yet. So another example that I see where people run into problems is computing a UCL 95. That's an upper confidence limit on the mean with 3, 4, 5 observations. And if the UCL happens to exceed the current maximum of your data set, then use the current maximum. And that's really not going to work well. A maximum might overestimate the UCL if you had 50 observations, but at 4 observations, it's very, very likely to be underestimating the UCL 95. The fact that your UCL 95 is higher than the maximum is an indication that your maximum is not very good. So you're going to be strongly underestimating the UCL with a maximum. Better guidance, more recent guidance, this I think was 2009, EPA's unified guidance document, define baseline conditions, get at least 8 observations, was usually 2 years of quarterly sampling, and then a lesser frequency after that, depending on the purpose, and that's key. So it depends on whether there are things like seasonality, seasonal variation present and all of that. But that unified guidance had a much better, more updated and modern guidance for number of observations, and this is still small. Here's another guidance document. This is from the ATSDR, out to State Health Assessors. I don't think it's in print yet, it's fairly new. And they based it on some simulation studies that they recommend that if you have 8 samples or fewer, don't bother to do statistics. You can do some plots. You could probably compute a mean of the 8 values, though you don't really have a good idea of how good that mean is. You're not going to be able to compute a standard deviation that's reliable, and so you're not going to be able to compute confidence intervals on that mean. You're not going to be able to compute percentiles with any, at least the extreme percentiles that people are usually interested in, like the 85th, the 90th, the 95th, 99th, None of those you're going to get good estimates for. Your software might give you back a number for them. If it does with 8 observations, it's wrong, because you really need about 20 to compute those extreme percentiles. Anyway, that's their guidance, and I think I agree with it almost exactly. From 8 to 20 observations, the best procedures generally are to assume a distribution, probably not the normal distribution, and then use the characteristics of the distribution plus the data that you've got to do estimates of things like means, UCL 95s, upper percentiles. You can do all that with statistics software. You can assume a log normal distribution, a gamma distribution. I talked about that 2 months ago in the webinar, and the webinar's up on our training site. You could go and listen to that, about fitting distributions to data. And in that case, it was for data with non-detects. And you can use these procedures with non-detects as well without sticking in a number for non-detects, but that's a different day. And above 20 observations, you can start to do the things you probably would like to do, bootstrapping, permutation tests, and other things. So the key is here that after you get 20, you've got some estimate of what the 90th and 95th percentile might be. You're starting to cover the range of the data out in the field, at least with some decent probability of doing that. So if you have too few data, what are the consequences? You probably won't be rejecting the null hypothesis of no signal, no trend, no difference from the standard in tests, no difference between the site that you're working on versus the background, that's the nice clean area. Those kind of things are going to be really hard with few data. And it doesn't prove that the problem isn't still out there. It's just that you haven't collected enough data to see it. So it produces false negatives in tests. It's difficult with 4, 5, 6 observations to decide which distribution to use. You should guess that it's going to be a skewed distribution and use things like the gamma or log normal. But if you're trying to compute prediction limits, tolerance limits, things that are up towards the upper end so you can compare individual numbers to them, you're going to probably underestimate standard deviations and underestimate the limit. And so as you go on and collect a few more data, it might show that they are now exceeding your computed prediction limit, not because they're really unusual or anything other than just part of the background data set, if you want to think of it that way, but you just didn't collect much data to do the initial estimation. So if you're comparing data to UCL 95s with 4 observations, your UCL 95 is probably going to be way too low. And you may collect in the future data that exceed it, not because there's been a change, but because you didn't collect enough data to start with. So just to throw a few numbers out here and move on. The UCL 95, you can expect it to be greater than the true mean, and you should be able to expect that to happen 95% of the time. If you have 4 observations, it's more like it has about a 72% chance of being higher than the actual mean. Not the sample mean, but the mean out in the field. 8 observations, about an 81% chance, and so on. So with small observations, your UCL 95 is not going to do what you want it to do. So what hasn't changed, I haven't yet got to what has changed. What hasn't changed is insufficient numbers of data. I think it's probably the biggest challenge in environmental science these days. The big research in statistics is on something called big data, which means huge data sets, usually things collected about you and your Facebook page and your online purchases, and that determines, they think, or at least gives a good classification for what you might buy in the future. So they use the same kind of big data procedures in genomics, so other places where they're just a mass of data, a huge amount of data that they want to make some sense out of the patterns. We deal with small data. And so the important thing is not to make it too small for what you're trying to do. Just mention again for the Mann-Kendall test for trend as a very simple and generally good test for trend. You won't find a difference. You won't find a trend. When you have fewer than 5 observations, that's physically impossible, numerically impossible is a better way of saying it. If you had 5 observations, they would have to be all aligned, all increasing, each one higher than the previous one to find a trend numerically. So you're probably going to be missing things a lot with the sample size of 5 and trying to do a trend with that. The original authors back in the 1980s of that test recommended that it should have at least 10 observations to run a Mann-Kendall test. And I don't know of anything that's changed since that. So what has changed in this? Well, not a lot. A little. First, you could read one of the new chapters in the second version of the book is on how many observations do I need. And there Ed Gilroy looks at the power of tests and uses that to determine how many observations you need for non-parametric tests versus parametric tests when data are skewed, and shows that there are fewer observations needed for the non-parametric tests. So you can take a look at that when it comes out. That's one of the ways to get more power with the same amount of data, is to use a better test. Another thing that has changed, I don't really like this, so I'll put that right up front, but some regulatory agencies, in order to get people to submit data to them that have enough observations, they assume guilt instead of innocence. So they assume that you're out of compliance unless you can prove otherwise, and that then puts an incentive on the people that are submitting the data to collect enough data to show that they in fact are below a standard. So again, I don't like that. I think that's more a sign of the sad state of data collection in the country, but and not just the United States, but elsewhere. So permutation tests should help a little bit by doing more efficient use of the same amount of data, but it really is it's helpful to all of us to collect sufficient data. And another thing that this problem has started to cause, and we'll talk about this in a bit, is that p-values where there's no signal found with small data sets are reported as whether it was insignificant that you would find these differences. When that's been done in the medical community, and then people in the media have picked up on that and made statements like this test that the medical folks did showed that there was no relationship between drinking coffee and cancer or something like that. That could be a very inappropriate conclusion to make, that people in the media who would then present it to all the rest of us, and so the general public gets a wrong understanding of what might be true based on this classification to insignificant and significant, especially when there's small data sets. And so that's had some blowback in statistics that we'll talk about in a minute. I'm going to do one more poll here right now as we move on to the third subject. So what should you do with outlier observations? And then you can pick one or more of these: to delete them, to look into them more closely, to value them highly, or nothing special, just use them like any other observation. Give you just a second more and we'll shut it down. Okay, let's take a look. 90% said look into them more closely, 13% value them highly, 16% nothing special, deleting them 5%. All right, well, I would say 95% of you were correct. If you answered anything other than delete them, it would be just certainly one of several appropriate approaches to outliers. So that message seems like it has gotten across more than the previous one. So that's good. That's good. That means I can go through this a bit more quickly, perhaps. So deleting outliers for no reason other than what you see in the data set itself is something you should not do. And so there's a variety of examples here on the left of when people have done that. I'll just look at the one in the middle for right now. This is an interesting one to me. So somebody developed a computer algorithm, probably computing the mean plus or minus 2 standard deviations. And if anything was outside of that, then that got deleted. Well, that's not a good idea. And so there was an increase apparently in temperatures in some cities, towns in Alaska, and the algorithms just threw all that data out. So it took a while for somebody to really realize what was going on. They didn't have any data from up there. So those kind of things are bad. Sometimes there's guidance that says to run a test. I will mention this. There are tests for outliers. The common ones are Grubb's test and Rosner's test, and there is guidance that says if it fails those tests, then just delete them. That's really bad advice. So you should be aware that there is no test for bad data in statistics. That outlier tests are not for that purpose. They are for the purpose of seeing if observations came from a normal distribution. They're basically setting up a model and then looking to see if the data fit that model. And a normal distribution model is a very unrealistic model for chemical concentrations in any natural media. So you should expect to see outliers. It's very common, and it's not a cause for throwing them away. In fact, they may be the most important observations in your data set. They might represent conditions you're not expecting. They might be kind of a combination of a couple of different, what a statistician would call a population, a set of data representing conditions. So you might have 2 sets of conditions you're putting together, and you might decide to split them up and look at them separately. It often can give you some clue into how the science works, how the system is working out in the world, and might lead you to some better understanding of it. So that's the benefits of outliers. You should definitely not throw them away. They can come from recording errors, skewed data, which is very common for us, data from a second population. So, and there's some quick statements about solutions for those things, but only where you have some evidence from outside of the data set, something from the science that you know about, would it be valid to remove them. So a statistician will not back you up if you say that you remove them because of the Grubbs or Rosner test. That's not what those tests are for. Why did people get into doing that? Probably because they were using t-tests and similar tests that assume normality, and those outliers didn't look like they came from a normal distribution. They increased the mean, they decreased the ability to see things because you were using, or someone was using the wrong kind of test back in the old days. But we don't have any reason to do that these days. And if you're truly interested in a mean, the mass, the total mass for the year, how much stuff has moved down the stream in a year's time, the load, some other measure of total amounts, spatial totals, cumulative exposures, those things should be affected by a mean. The mean is probably the most valuable point in the data set. And understanding why it was high in that point is probably a very valuable thing to do. So they don't necessarily indicate an error. So what has changed? One thing has changed is that people outside of statistics have become aware of this, and outside of environmental science have become aware of this. And recently, from what I've seen, lawyers have become aware of this. And so a scientist that has thrown out some outliers and the lawyer didn't like the result often questions that person fairly hard these days. Why did you delete those outliers? And so it's important to know, well, who's there to back you up by doing it? So here's the statement from the former chief statistician of USEPA. There are a lot of statistical methods looking at whether an outlier should be deleted, and I don't endorse any of them. Or a reputable statistician who used to work at the USGS, Ed Gilroy. One of my favorite quotes of all times, as a matter of fact: treat outliers like children, correct them when necessary, but never throw them out. And then in 2014, there was an editorial about this subject. This Outliers had a prominent part in the editorial, but some other things that she found it to be not good science, articles that were submitted to the journal of Science, one of the more reputable journals in the scientific community. And she gave us an example that clearly throwing out a few of the data points by declaring them outliers in this particular case would have improved the fit to whatever model they were trying to use or a distribution they were trying to use. But they resisted the temptation, and it was not too long before it was realized that these outliers were a key to a much more complete understanding of something in the science that they were doing. So I used to know stuff about oceanic plates, but it's been even longer than 40 years. So I'm not there anymore. So throwing outliers is not going to be supported just based on the data set you happen to have collected. You have to have reasons from science to do that. Okay, over-reliance on p-values. This is the fourth change. And the p-hacking is something that people do. The term's relatively new, but people have been doing it for a long time, and that hasn't changed. So one of the main issues is that p-values are a function of sample size. And if you don't have much data, you won't see things just because you don't have much evidence. So taking that blue arrow to the left, if someone takes that and says, well, we did not find a trend, therefore there is no trend. That's an inappropriate conclusion. You can't prove that because you don't have enough data to prove anything, really. So a large p-value doesn't really prove anything about a null hypothesis. It just says it might be the result of not having much data, or it might be a result of using tests with low power. So that's one problem with p-values, is how they are interpreted. I'm building to the fifth thing, which is how the public sees statistics and how statisticians have reacted to that. And one of the things they've reacted to is these misconceptions, because in part, statisticians have developed these things. You and I as scientists have used them, but not always correctly and not always spoken about them correctly. And now the public's gotten the wrong idea. Okay, back to this. The red area, lots of data. If you have a lot of data, you can always reject the null hypothesis. The p-values get tremendously small if you have thousands of data points. And then very small things that might be very minor and unimportant, that's the important word, unimportant trends are seen. And so those would be declared as significant. And so significant statistically is not practical usefulness. It's not the same thing. You may find things with a lot of data that are really so small, you know, a 0.01% change per year trend, that it doesn't really matter for the ecosystem or human health or anything else. But it's significant. And again, people get the wrong idea when you attach that word to it. So it may not be important, even if it's significant. So keeping that straight is going a long way towards keeping p-values in their proper perspective. Sometimes, though, people need to get a p-value that's small and reject the null hypothesis so that they can get their paper published, and that's the journal's fault. And this is called p-hacking. So here's just a simple idea of that. A cartoon, there will be a cartoon in the Statistical Methods in Water Resources book, and so this is it, where the stick figure coming in from the left gets all excited, jelly beans cause acne. And so the other stick figure, the bald stick figure, says, okay, scientists have to investigate. So there's 20 different tests that are run, apparently. Well, actually, initially, they just do a test of, do jelly beans cause acne? And the result is that the p is greater than 0.05, so it's not significant. So no, they don't. And you can see the stick figure looks like they have goggles on. I guess that's supposed to indicate being a scientist at that point. And so he says that settles that. And the other one says, I hear it's only a certain color that causes it. So now it's back to test it again. So now 20 tests are done for 20 different colors of jelly beans. 19 of them show no relationship, but one of them has a p-value less than 0.05, the green jelly beans. And so the news media says green jelly beans are linked to acne. Okay, so that's p-hacking. If you have an alpha of 0.05, if you've made that cutoff, then you would expect that 1 in 20 tests will erroneously reject the null hypothesis when out in the real world it's not. So you can't just keep trying doing multiple things until you finally get a significant result. That's one of the problems with p-values. So how is this changing? I say this might change because it's still in its early stages, but it certainly seems to me that it's trending that way in statistics. So that's to get rid of, and I don't know how coercive this is going to be. There are people that are talking about making sure that all journals know, their editors know, that they should never allow a paper that uses the word statistically significant or insignificant. And I'm serious, that's what they're saying. So your relationship with p-values might change. So the recommendations are going all the way from reporting a p-value but get rid of a cutoff like 0.05 or any other cutoff, down to not reporting p-values, not reporting statistically significant and insignificant terms. So that would be a big change. Why do they argue with that? Over on the left, and there we go, I've got my cursor back, that things like 6% and 4.5% are not very different, and yet they're on either side of that 0.05 boundary. So people should realize that p-values are a continuum, and that 0.06, because it gets labeled insignificant, is not all that different than 0.045 that's labeled statistically significant. We talked about this practical usefulness, and that reporting things significant is understood as important when the effect size, that what it's actually causing, might not be anything to be concerned about. And then the recommendations are generally, the cause is about misinterpretation by the press and the public. It's been giving statisticians a bad name, I guess, that treating statistical results as being the only measure of an evaluation of your data is not a good thing. And so the recommendations coming out these days are more along the lines of bringing in other outside factors, looking at p-values as only one piece of evidence among a number of other things. And that's been taught in our applied environmental statistics class for at least a decade, if not longer, I know, but it may seem new to some of you. So bringing in outside other evaluations in doing things like selecting which X variables go into a regression equation and all of that is becoming more likely to be the recommendation in statistics. So you should pay attention to that and try to keep up with it. All right, another way that people have adapted to it is by, and I'm running out of time here, adapting to it by other kinds of procedures. So I'll just talk about this first one. WRTDS is a smoothing kind of procedure developed by Bob Hirsch and others. And so on the left side, the graph here shows that when looking at mercury concentrations in a river, over a long period of time. The older period was the black line. The newer period, 20 years later, is the red line. And you see things have changed a lot at the low end, the low flow end, low discharges, but nothing much has changed at the upper end. And that kind of difference is something that you might not have seen if you'd just done a regression or a Mann-Kendall test for the entire data set. And so they're using smoothing procedures to try to show these patterns. Here, the change in color at the low flow, it's down at the bottom on the right-hand graph. It's changing from grays to whites is showing this drop in concentrations. So giving you ways of evaluating what's going on your data set without sticking a p-value on it. So smoothing methods do that. Just a couple of weeks ago, I was at a conference and a number of people were doing things called regression tree methods in groundwater quality. And again, this is just another type of procedure that doesn't depend on p-values. It evaluates the goodness or badness in terms of how what percent correctly classified data do we get? So it starts out with some concentrations, splits them into categories, and splits them by values of cutoffs of explanatory variables. You may do that for several different explanatory variables. At the end, the concentrations get put into categories, and you can get probabilities of what you're in, what category that concentration might be in. So these explanatory variables might be input as GIS coverages for spatial things. The procedures will give you back relative rankings of which variables are more important, meaning which ones contribute most to the good and bad classifications, and ends up presenting it on maps. So there's a lot of this type of work. None of it has to do with p-values. And it has other advantages over things like regression in that you're not limited to a straight line relationship. So with regression, things at the upper end of the regression line might be strongly influencing the prediction down at the low end. And these kind of procedures, whether it's the smoothing or regression trees, don't have that problem. So that's just an example of the way things have been moving. And then finally, the last one, using Excel for statistical computations. Excel is not a statistics package. It's better than it used to be, but still almost everything I do can't not be done in Excel. Now that might be slightly different for you, but still much of what you should be doing cannot be done in Excel. So it's just that it doesn't do a whole lot. There used to be a lot of things that were wrong in the statistics, in the mathematics of their procedures. And in 2008, they improved a number of those. There's still a few things that it doesn't do correctly, primarily related to regression and evaluating regression equations. But the main thing is that Excel just doesn't have the newer methods that you would routinely use. There are add-ons you can buy that would. There's other software that you can buy or get for free that would. But Excel in and of itself doesn't have a lot to use. So the other things that are available, what has changed in the last 40 years is software. I'll start at the bottom. R is free. It can do anything you can think of. It does it well. Its only problem is that it has a learning curve. It takes a while. It's really a programming language, and it takes a while to learn it. And it's pretty similar to another statistics package called SAS in that regard. There are pull-down menu ways of dealing with R, but you end up doing some typing. So that challenge, that learning curve for someone that's not a full-time statistician, but only uses it twice a year, is real. And that may not be the best approach for you. One of the others might be commercial software. They're currently putting in a lot of these new methods, bootstrapping and permutation tests. Some of the software does have it, and that's something you should look for. If they're there, then the pull-down menu system is no harder to do those than it was for doing t-tests. And so you should look at some of the software packages and evaluate them for yourselves. These cost something. They save you a huge amount of time. Then here's one that I recommend to people. It's free. It has pull-down menus. It has permutation tests and bootstrapping. It has good regression diagnostics. It has even some multivariate methods that ecologists use. It's called PAST. And it's free. You could go and download that. Just go into your browser search and type in statistics and PAST, and you'll find it. So I recommend that for people that are only doing statistics twice a year and don't want the challenge, and it is a challenge of learning a more complicated package, and it works really well. It's probably biggest downside is getting the data into the package. The easiest way is to cut and paste. And what else has changed is down at the bottom. Pick up the second edition of the book when it comes out. We've used R there for all examples, and we hope it will be a way for you to learn how to use R. Every figure and every example that's worked out in the book, you can go and download the code, the lines of code to do those things and then model what you want to do after them. So in summary, use permutation tests and bootstrapping. You'll miss things if you continue to use the older tests. Collect ample data. Don't delete outliers unless you have evidence outside of the data set showing that they're in error. Don't p-hack or over-rely even on p-values. Understand that your data using graphical procedures, and incorporate other data. And then use modern statistical software. If R is too complex, try PAST. And download a second version of the book. I've said that a couple times. When you end this webinar, you will get an opportunity to sign up for our announcement newsletter list. If you're already on the list, and I'm sure a lot of you are, then just ignore it. But if you would like to sign up, you have an opportunity there to do that. And you'll get back an email that has you click a link to opt in. Okay. And that way you'll get notice when the book is available. Otherwise, just look on our website, Practical Stats, and it'll be displayed there when it's available. Our next month's webinar is Tuesday, May 21st at the same time, 11 a.m. Mountain Time. And since I'm in Mountain Time, I'm going to use that. And the topic, I don't know yet. I've got some ideas. Probably my primary idea right now is doing multiple regression with non-detects, but I may decide to do something different. So I will announce that. I will put it up on the web with the link to sign up, just like you did this one, on our webinar page sometime in the next few days once I make a final decision. Or if you sign up for the newsletter, you'll get the email that says, here's what I'm doing, and here's the link to sign up at GoToWebinar. Okay. Or you can just go to the webinars page every now and then and take a look to register and find out what it is. So not everyone who signed up was able to attend. Maybe they don't want to attend either now, but was not able to attend. And so if you know some of those folks, they should within an hour from now be getting a link that will tell them where to go and be able to stream it. If you know other people that missed it today, just give them this link at practicalstats.teachable.com. That's our training site. You might have to scroll down to get to the free stuff, but it's down there, including this webinar and the past webinars that I've done. So thank you for attending. I have done it in an hour, but not left time for questions. So I'm going to take another 10 minutes for questions. However, if you don't want to stay, that's fine too. So let me take a look at some questions. While permutation tests are distribution free, aren't there still test-specific assumptions that must be satisfied to use a specific permutation test? The really only assumption in the permutation test is an assumption that you make when you make the null hypothesis. So the assumption for a permutation test is that any of the data that you have collected could belong to any of the groups, which is just another way of saying all the groups have the same characteristics. It's just all one set of data. So that's the assumption for a permutation test. Doesn't have any others. Obviously, if there's two group permutation tests and more than two group permutation tests and that kind of thing, but that's your data structure and how you've collected it. So it does not have an assumption about a distribution. One of my colleagues asserted that parametric methods are more precise than non-parametric methods. How can I respond to this in a compelling way? Tell them that that was disproved in the 1950s and 60s. You could also say that when those statements are made, it's based on things like this, where someone has generated data from a normal distribution. And in that case, a normal distribution-based method has about a 3 or 4% advantage over a non-parametric method. That's a really small number. For you, you don't have data from the field that are generated, and so you don't have anything like that. And the best case scenario in the field is that things look approximately normally distributed, that there's points around the straight line on a Q plot. And in that case, they have the same power. If they look as best you can tell like a normal distribution with some noise, that's enough different from a normal that they have equal power. And if there's any evidence for skewness at all, then non-parametric methods have more power. The big cause of skewness in the data that you collect is a lower bound of 0. So for things that are down close to 0, so that it doesn't make sense that you could go 2 standard deviations below the mean because you're going to hit up against 0 before you get there. If you see negative boundaries on the lower confidence interval, on the lower prediction intervals, those kinds of things. That's all evidence that the data are strongly skewed and your t-tests and ANOVAs are not going to work well. There's plenty of books that have statements in them about this as well. So they're just not in the one semester textbook that you get in college usually. You mentioned that bootstrapping to attain a confidence interval on the mean does not assume normality. Due to my inexperience, this confuses me. Doesn't the mean inherently assume a normal distribution? No, it doesn't. The mean itself is a number, and it's the center of mass of the data, which means that if you have one point that has all the mass in it because it's a huge number, like a big whopping storm moving sediment down the stream, it may be one day per year and it puts out 80% of the mass for the year. The mean is going to be averaged over the 365 days. So the mean is not typical, this would be the word I would use. It's not necessarily the median. It's not necessarily a frequently occurring value. It may be very atypical, affected by one number or two numbers. But it has nothing to do with a normal distribution per se. It's when you then compute a confidence interval around that a t-interval method using a t-statistic does assume a normal distribution, or you have enough data to overcome the non-normality. And the number of data that you need for the type of skewness that we have is something along the order of 70 observations. Okay, just skip down a little bit. And again, I will have answers to all of these later. Is there guidance available on the relationship between number of observations necessary and the length of time over which observations are collected? For groundwater, I would expect you to need data for a certain number of years to see a trend. Is there guidance available for that? Sure, there are. Let's see, some of the things I've seen online. There's the ITRWC or something like that. It's the interstate guidance group, basically, for groundwater studies. It's not what their name is, but it's something like that. They do a pretty good job. It's been a while since I've looked at it, but they do a pretty good job for giving you those kinds of guidance values. That when they get into the areas of statistics, they do pretty well. So that would be one place. And then there are plenty of state and federal guidance documents, and I would just stick to newer ones rather than older ones for their recommendations. Okay. Why do guidance documents recommend outlier tests, and why should we perform them at all when in most cases we shouldn't delete statistically identified outliers? Thank you. Great question. Why do they recommend them? Probably because they learned them in school themselves. The people that write guidance documents don't necessarily have any more training in statistics than you do. Depends on the guidance document. And they may have their training in statistics that's quite outdated at this point. So it does, the outlier tests, I don't know, I think that you could do just as well with graphs. Looking at outliers does raise them to your attention, and then you could go and see if there's any evidence outside of the data set for why they might be wrong. That's certainly a valid thing to do. And if you find that there's some problem, delete them. If they represented a particular time when the quality assurance wasn't all that good, then delete them. So it's nothing wrong with identifying them. It's just what you do with them. That's the issue. If you want to identify them with a test, I suppose you could. I think I would recommend taking logs first, because since most things are skewed, and these tests assume non-skewness, they assume normality. If you take logs and then run an outlier test, it might give you a more reasonable measure of which things look odd versus which don't. Let's see. Last question. What about Excel add-ins such as Analyze It for statistical testing? The add-ins vary. I haven't looked at them in a long time. I've twice over the past 20 years did an evaluation of them. You'll find all of that in the newsletters that are up on our website. So I think the last time I did it might have been like 2000 and I'm guessing 2007 or 8. So 10 years ago, so things could have changed. I found a couple of quite good ones for add-ins to Excel. So it's certainly one way to go. I would look and see if they've been evaluated by someone else, and I'd run some data sets, if you can at all, through a standard statistics package, one that you've paid for, and then run it through these and test it out and see if you get the same numbers. And that would be a test for those things. Or ask them before you buy it if they have done that. So there are some testing data sets that statisticians use all the time. So having something other than just their website, I would go on. But you can certainly look at the recommendations that I gave back 10 years ago or more if you'd like to on our newsletter page. And so with that, I will say thank you. And you should be able to get to sign up for the webinar list and the announcement list, the newsletter list, whatever you want to call it. And I'll talk to you next month if you so desire. Talk to you then. Thank you. Goodbye.